In this lecture, I want to talk about what happens when we bring data into the cache. How do we decide where in cache to put the data? How do we know what data we currently have in the cache? And when we have to kick something out, how do we decide what data to replace? We've seen how to analyze C code or assembly and determine whether data will be read or written by various operations. So for this lecture, we'll take as our starting point a sequence of operations that interact with memory, where each operation will be either reading or writing data, and we know for each of those operations what address we are reading from or writing to. We also know that the cache sits near the top of the memory hierarchy, so when we are accessing data, if there is a cache hit, then we will only be accessing the cache, whereas if there is a cache miss, we will have to bring data into the cache from a lower level of the hierarchy. And we know that when we move data from the RAM into the cache, we will bring data a block at a time. The first step in reasoning about our sequence of memory operations is to translate the addresses from hex into binary. We normally display memory addresses in hex because that makes them much more human readable, but here we need them in binary so we can think about how the different bits of the address get used to determine how we place the data in the cache. The next thing we need to know is how big a block size we're using when we transfer data from RAM to cache. Just like any storage medium, the cache is fundamentally storing a big sequence of ones and zeros. But it will help us to logically organize the cache into chunks that correspond to the blocks of data that we're moving around. And so fundamentally, we think of the cache as being divided into some number of lines, where each line stores one block of data. So the next thing we need to know is the size of blocks we're using, which will determine both how much data we transfer at a time between the RAM and the cache, and how much data is stored in each line of the cache. For now, we'll assume that we're working with 32-byte blocks, and therefore each line contains 256 bits of data. But this block size is something that can vary on different architectures. If we perform a read operation accessing the data at address FD54, we first need to determine whether the data we're looking for is already in the cache. And so we need some system for tracking which blocks of data are currently in the cache. And this is part of what gets stored in the cache metadata. So associated with each line of data in the cache, we also have some metadata for that line. Because the cache is so much smaller than the RAM, we need some way of keeping track of which blocks of data are we currently storing in any given line of the cache. The simplest way we could do this is by just storing in the metadata what address we brought into that line of the cache. So if we take, for example, this first read operation, we're looking for data at the address given by this binary number, but we know that each line of the cache contains an entire block's worth of data. But the system ensures that when we transfer blocks of data around, those blocks of data are always aligned to addresses such that we can view the last few bits of the address as an index within the block. So if our blocks are 32 bytes, then there are 32 addresses within each block. And since there are 2 to the 5th addressable bytes within the block, then we know that the last 5 bits of any address specify which position within the block we're accessing. And so in this case, we can consider the last 5 bits in this address the offset within a block. And so if we access any address that has these same first 11 bits, then we will get the entire block corresponding to all 32 possible offsets that have the same first 11 bits. And so if we bring this block into the cache, and let's say that we put it in line 3 of the cache, we bring in a 32-byte block of data and put it in line 3 of the cache, and this block will contain all of the offsets from 5 zeros up through 5 ones. And so that we know in the future which block of data is in line 3 of the cache, we can put the rest of the address, the part that is common to all of those addresses, into the metadata. The high order bits that identify which block of data we have brought in is called the tag, and so we can store the tag as part of the metadata for this line. Then on future operations, before requesting data from the RAM, we can check whether the tag that's stored in the metadata for any of the lines of cache corresponds to the tag for the data we're looking for, in which case we know that the address we're requesting is somewhere in this block, and we can determine where based on the offset bits. So on the next operation, when we're writing to FD56, when we translate that address to binary, we find that it has the same tag as the previous address. And so when we check whether this tag is currently in the cache, we will find it, indicating a cache hit, and then we can use this offset as an index into the block of data to find the particular bytes that we were trying to write to. So far, what I've been describing is known as a fully associative cache. In a fully associative cache, any block of data can go in any line of the cache, and so if we're trying to check whether the data we're looking for is already in the cache, we have to match the tag for the address we're seeking against the tag stored in the metadata for every line of the cache. And if any of them match, then we know that the line where we found a match is a cache hit. But if all of the tags are different, then we'll need to request the data from the RAM. In order to ensure that checking the tag against the metadata for the different lines is fast, this is implemented in circuitry, and the circuits can check the tag in parallel for all of the lines of the cache. But doing that requires a lot of circuitry to be able to run these checks in parallel for many lines. And so sometimes it's worth it to not have a fully associative cache, but instead have a direct mapped cache, where a block of data goes in one specific line of the cache. In a direct mapped cache, it will still be the case that we will bring in blocks of data, and so the low order bits of the address will refer to an offset within the block. But now, to avoid having to check every line of the cache, we want to use the address bits to tell us exactly where in the cache do we want to put the data. In this case, since our cache has 16 lines, we can use 4 bits of the address to specify a number from 0 to 15 and tell us which line of the cache should we put the data in. And so we would use the next 4 bits of the address to specify an index into the cache. If we're using a direct mapped cache, when we read from this address, we can use the index bits to determine which line of the cache would the data be in if we had previously brought it into the cache. So here, the index bits are the number 2, and so we can go to line 2 of the cache and check whether the data that we're looking for is there. We still could have many different addresses that might appear in that line of the cache, and so we still use the remaining high order bits of the address as a tag to distinguish what's currently in that line. And so here we would compare the tag for the data that we're looking for against the tag that is currently stored in the metadata for line 2. And if that's a match, we have a cache hit. If the tag doesn't match, then it's a miss, and we have to go get the data from RAM. If we bring the data in from RAM, then we will store the tag in the metadata for that line of the cache. Note that in this case we have less metadata to store because we have less to disambiguate, since we know that the only blocks of data that would go in this line are ones that have index bits 0010. So we don't need to store that portion of the address in the metadata. But as we proceed with our program, if we get to this read operation that is accessing address 5042, we can think about how that translates into tag, index, and offset. When we read from this address, we split it into tag, index, and offset, and our index is 2, so we will check line 2 of the cache and see if the metadata tag that we've stored matches the tag for the address we're looking for. In this case, it doesn't, so that means that we have a cache miss, and we need to go retrieve the data from the RAM. And when we bring that data in, we will overwrite this line of the cache with the new data that we read in, and we'll update the tag to the new value of the tag for the data that we just put in that line. So direct mapping makes the check of is the data we're looking for in the cache much simpler, because we only have to look in the metadata for one line. But this illustrates a potential problem where if our program were going back and forth between accessing these two addresses, then each time we accessed FD54, we would kick out the data at 5042 and vice versa, and so we would get a large number of cache misses, even if these were the only two addresses we were accessing, because by mapping them to the same line, we are kicking the data out prematurely. So a compromise that gives us the best of both worlds, where in fully associative we have fewer problems with kicking out data that we might use soon, and direct mapped cache, where we have less work to do to find out whether the data we're looking for is present, is called set associative caching. In a set associative cache, we split the lines of the cache up into sets, and we use the index to determine which set the data should go in, but then we allow a block of data to go in any of the lines that are part of a given set. So for example, we could break this cache up into sets of size 2. This would be a two-way set associative cache. We could alternately have a four-way set associative cache where we group 4 lines together into a set. But we always want the associativity to be a power of 2 so that we can use some subset of the bits to index into the sets that we've divided our cache into. If the cache is set associative, then again, reading from address FD54, we still have the same block size, and so the 5 lowest order bits are still an offset. And now the number of bits we'll use for the index is determined by how many sets we have in our cache. Here we have 8 sets, which is 2 to the third, and so we'll need 3 bits to tell us which set the address belongs to. We still refer to those bits as the index and the remaining bits as the tag. But now, instead of telling us a line number in the cache, the index is telling us a set number. And so with an index of 0, 1, 0, we know that if the data is in the cache, then it must be in set number 2. And so if it's present, then the metadata for one of these 2 lines would have to hold the tag corresponding to the address we're looking for. And so then if we bring the data into the cache, we have the option of putting that block of data into either of the lines that are part of this set. We don't have the freedom to put the data anywhere like we did under a fully associative cache, but we're not required to put it in exactly one position like we did under direct mapping. And in this case, we have an 8-bit tag that we need to store as part of the metadata. Now, when we continue through our operations, the next operation will have the same tag, and so we will check whether that tag is present in either of the lines in the set, and it is, so we have a cache hit. That was much easier than checking every line like we had to do for fully associative, but slightly harder than we had to do for direct mapping, where we knew exactly which line to look in. But when there's a hit, we can just use the offset bits to tell us where within that block of data is the position that we're writing to. And now, when we read from 5042, we split that up into tag, index, and offset for our set associative cache. Here again, we have an index that corresponds to the data that we had previously brought into the cache. And so we'll go look at that set index, and we see that neither of the tags matches. And so we'll have to bring in the data from this address in the RAM. But when we bring that data in, we're no longer forced to kick out the data that we just accessed. We could instead bring the data into line 5 of the cache and update the metadata for line 5. Each of these schemes gives us a way of determining where in the cache can we put any given block of data, which then constrains for us where do we need to look if we are trying to figure out whether the data we are seeking is already in the cache, and what options we have for which data to kick out when we bring in a new block from the RAM. So far, I've been talking about the question of where to put a block of data as a decision that we can make, but fundamentally, that decision needs to be implemented into the hardware that actually manages the cache within the CPU. So this is not a decision that we can make on an ad hoc basis. We need to program into the circuitry the way that cache replacement happens. And so to get good performance out of our cache, we need to keep track of some additional information in the cache metadata to help with this cache replacement policy. Let's focus for now on our set associative example, and suppose that we just performed this sequence of memory operations. We first had a memory read that was amiss, and so we brought data into the cache and put it in the first line of set number 2. Then we did a write operation, which was a cache hit, and so we modified some of the data that was in this line. Then we had another read operation, which was again a cache miss, and we brought the data in, and it went to the same set, but we were able to put it in the other line of that set. Now suppose that we have yet another operation that brings in data with a tag of 010. Now we have a question of which of these two lines should we overwrite with the data that we're bringing in by this new operation. The terminology here is that before we can bring in the new data, we have to evict one of these two cache lines. And fundamentally, a cache replacement policy is a rule for deciding which line of the cache to evict when we need to bring in new data. The ideal replacement policy would predict which of these two blocks is going to be needed again sooner and keep that one in the cache. But obviously that's not possible to do in general, so instead we want to use our history of accesses to make a reasonable prediction about which line is more likely to be used soon. And based on the idea of temporal locality, we can make the guess that the block which was accessed longest ago is least likely to be used in the near future. And so in this case, based on our order of operations, we'd like to kick out the block that was used least recently, which was the block in line 4. But how can we keep track of the information about which was least recently used? Well, if we have a two-way set associative cache, then we can just keep track for each of our sets which of the two lines has been used less recently. And we can store as part of the metadata for each set which of the two lines within that set is least recently used. For example, here, when we read and then wrote the first line of this set, we could set the LRU bit for this set to 1, meaning that the more recently used line was line 0 out of the two, and line 1 was least recently used. Then when we do a read operation that puts data in line 5, we could update the least recently used bit to 0, indicating that line 5 has been used more recently than line 4. And now when we come to a new memory operation that needs to put data into set number 2, we can check the least recently used bit and say, aha, based on this information, I know that this data is older in terms of when it was last used, and so it would probably be better to overwrite this line with the new data that we're bringing in, and so we'll choose line 4 to be evicted. But before we can evict line 4, there's an additional complication that we need to worry about. The second operation that we performed on that block was a write, which means that at offset 22 within this block, we updated some bits. And that means, because we wrote to this line of the cache, that the data in the cache is more up to date than the copy of that same data that lives in the RAM. This is a consequence of the cache write policy. In principle, one could design the cache such that every time we wrote an update to a line in the cache, we would also send that update to lower levels of the memory hierarchy, including lower levels of cache as well as the RAM. That would be known as a write-through policy, because every time we do a write, it carries through to all of the levels of the hierarchy. But the much more common policy is known as write-back, which is you only send writes to lower levels of the memory hierarchy when you are evicting data and sending it back to those lower levels. A write-back policy is much more efficient because we don't have to wait for the update to propagate all the way down to RAM. We can just make our changes in cache and continue executing. But this means that when we evict this line from the cache, we need to send the updates that have been made down into the lower levels of the hierarchy, whether those are lower levels of cache or down into the RAM. But because that operation of propagating the changes down through the memory hierarchy is slow, we'd like to avoid it when we can. And so if we had a line in the cache and we only ever read that line, we never updated the values that were being stored in that block of data, then we know that the copy we have in the cache is still the same as the copy that was in the lower levels. And so we don't actually need to write it back and wait for that operation to complete, which means that we need another bit of metadata to help us keep track of whether a line has been updated since we brought it into the cache. This is known as a dirty bit, and when we bring data into the cache, we initialize the dirty bit to 0, meaning that this data has not been changed since we brought it into the cache. But as soon as we write to data that is in the cache, that data has been changed, and so it is now dirty and will need to be written back if we evict it. And so this write operation is a hit. It modifies the data that's in the cache, and now the data in the cache is more up to date than what's at lower levels, and so we need to change the dirty bit to 1. Then, when we subsequently evict this line from the cache, before we write over it, we can check, is the dirty bit 1? If so, we need to pause and ensure that the changes get sent down the memory hierarchy so that they aren't lost. And when that's complete, we can then proceed to overwrite. Or if the dirty bit was 0, then we know that we don't need to wait and we can just overwrite it immediately. It's also common for the metadata to contain a valid bit. The job of the valid bit is to tell us the thing that I've been illustrating by just leaving things blank, which is there data there at all? Specifically, when your program starts running, none of its data is in the cache yet, and so the bits that are in the cache are garbage from the perspective of your program. So when we start a new program running, we need to set all of the lines of cache to invalid by setting their valid bits to 0. And then when our program starts bringing data into the cache, it will set the lines that it is using as valid by marking their valid bit to 1. And that way we know whether the 1s and 0s that are in the cache are actual data that belongs to our program or just garbage that happened to already be there. We don't want to check the metadata and see a tag that matches that was just coincidentally matching based on something else the computer had done previously. The valid bit can also be cleared if the operating system swaps which program is running on the CPU at a given time, but we'll talk more about that when we get to processes in the near future.